Chapter 4, Think and Rank. All right, so the first one, boxes of varying masses are on a friction-free level table. First off, that bit right there, it's a level table, which means we're not dealing with any angle. There's no natural inclination for it to flow one way or the other. Weight is acting straight down. Normal force is acting straight up. They're going to balance each other out, so there's no acceleration up and down. All the acceleration is left and right. So rank each of the following from greatest to least based on A, the net force. Now, they don't define a positive or negative direction here. If we assume, so we need to assume either we're talking about to the right is positive, or we're talking about to the left is positive, or he's looking for ranking the magnitude of the forces. So in terms of magnitude of forces, or just adding the forces, remember they're in opposite directions. So if I have 10 newtons going this way, and I have 5 newtons going that way, well, let's choose a positive direction. Let's choose to the right positive. And so therefore, we have 10 plus negative 5, which is 5. So A has a net force of 5 newtons acting on it. B has a net force also of 5 newtons because we have 15 minus 10. C also has 5 newton force acting on it because we have 15 minus 10. And D has 10 newtons of force because we have 15 minus 5. So the net force on each of the boxes, based upon the magnitude, D is the greatest, and then A, B, and C are all tied. So that's based on magnitude. Now, if we choose to the right positive, it's the same ranking because all those were positive numbers. If we choose to the left to be positive, then what we end up with is D is the smallest because it's negative 10. If you want to feel like negative 5 newtons is greater than negative 10 newtons. And so that gets into some tricky language there. The intent is magnitude of force. Now, acceleration is you take that magnitude of force that we just had and divide by the mass, because acceleration is force divided by mass. And so for A, we have 5 newtons of force divided by 5 kilograms. We have 1 meter per second squared. B, we have 5 newtons of force divided by 10 kilograms. So that's a half or 5/10 meters per second squared. C, again, we have 5 newtons divided by 5 kilograms, 1 meter per second squared. And D, we have 10 newtons divided by 20 kilograms, or 10/20ths, or 1/2 meter per second squared. So in terms of acceleration, A and C are the same. B and D are lesser magnitudes of acceleration. In 55, all 3 cases, A, B, and C, the crate is in equilibrium, so no acceleration. Remember that equilibrium means acceleration is 0, it means change in velocity is 0, and it means the total force is 0. So rank them by the amount of friction between the crate and the floor from greatest to least. Since it's an equilibrium, we have the force pushing to the right, we have friction acting opposite direction of movement, and we have weight acting down, normal force acting up. So weight and normal force will balance each other out. The force in which they're pushing acts against the friction. So if they're in equilibrium, A, she's pushing with 100 newtons of force. That has to balance out a 100 newton friction force. B, 120 newton force she's pushing has to balance 120 newton friction force. And C, 130 newtons balancing out 130 newton friction force. Notice that the velocity of the objects, or the speed as is written down here, is irrelevant. Equilibrium has nothing to do with velocity. It deals with change in velocity. So it's ranked purely upon the C, B, A. 56, a 100 kilogram box of tools is at locations A, B, and C. Rank them from greatest to least based upon the masses. The mass doesn't care about where the object is, and so the mass of the object is the same. And there's another video on mass versus weight where I talk about that. So for A, masses, rank them based on the masses, it's the same. B, on the other hand, the weight depends upon the acceleration due to gravity. And so the larger I'd say larger the object, there's some other factors involved, which we'll get to in chapter 9, I believe it is, either 9 or 10. And so if you know the acceleration due to gravity on Earth, on our moon, and on Jupiter, then you're good to go. Jupiter has the greatest acceleration due to gravity. That's 24.5 meters per second squared. Earth is the next at around 9.8 meters per second squared, and our moon is about 1.6, 1.7 meters per second squared, somewhere in there. And so ranking on weight, it's going to be C, A, B. And then 57 I've dropped, so we're not worrying about 57. All right.